It's my pleasure to introduce Sylvie Corteel, and she's going to tell us about Rogers-Ramanujan identities and cylindric partitions.
So good morning, everyone. And I guess I'm really happy to give this talk, but I'm also pretty sad that I'm not with you in person. But that's how it's been for the last couple of years. So 2 years ago, I was basically planning to give you the same talk and thinking that in 2 years, I would have made a lot of progress. But as you'll see, other people made progress. So I'd like to dedicate this to all the women who had kids during COVID and are still standing up, because it's been a rough 2 years for me, and I'm sure a lot of others. Okay, so anyway, let me tell you about this new way to see Rogers-Ramanujan identities using cylindric partitions. And I hope it's going to inspire you to help me or help others or yourself solve this problem that's still quite open. So let me start by saying that this idea to start to look at these Rogers-Ramanujan identities using cylindric partition is not due to me. It's due to Omar Foda and Trevor Welsh, who started that in 2016. And they did that using mostly mathematical physics ideas. So then I looked at that from a combinatorial point of view. And with Trevor Welsh, we showed how to generalize this line of work to some A2 Rogers-Ramanujan identities. And then we started working with Johan Does and Ali Unku to generalize to some extent what we were doing and made a tiny progress. But recently there were 3 very new papers. The first one due to Ole Warner that appeared in 2021. And during the last couple of months, a paper by Kanade and Russell. And last week, a paper by Sue Chioka, who appeared on the archive. But you'll see, even though I will tell you about these very recent papers, okay, there's a lot of things that we still don't understand. But before I give you the open problem, let me start with the setup of the problem. Okay, so this is the whole team. And now let me go to introduce the objects. So even though most of you probably know, okay, my main object during this talk are going to be integer partitions. So a partition, lambda, here, is going to be a sequence of non-increasing integers. And we say that it's a partition of n if when I sum all these integers, then I get n. So for example, my favorite partition could be 4, 3, 1, and it's a partition of 8. Okay. So this is when I have one integer partition. But sometimes I'm going to have sequences. Oh, okay, before I say that. So now often I'm going to be interested in computing generating functions for the objects. So if I fix a countable set S, okay, and I want to sum on all the partitions, such that the parts, the lambda i's, are all in a set. And then Q to the sum of the lambda i's, the weight of the partition. Okay, we all know that we always get a nice product. Okay, the product I in S of 1 over 1 minus Q to the I. Okay, and often for the Rogers-Ramanujan identities, for example, I could choose S, the integers that are, for example, 1 or 4 modulo 5. Okay. And so sometimes I'm going to also look at sequences of what is known as interlacing partitions. So now I don't have just one partition, but I have a pair, lambda and mu. And I'm going to say that lambda interlaces with mu, and lambda is greater or equal to mu. If I can take the parts of lambda and the parts of mu and put them together, okay, and get a non-decreasing sequence, sorry. So that means that lambda 1 must be greater or equal to mu 1, greater or equal to lambda 2, greater or equal to mu 2, etc. Okay, so an example that I wrote here is that 4, 3, 1 is interlacing with 4, 1, 1. okay, because 4 is greater or equal to 4, greater or equal to 3, okay? So I can take the parts of lambda and mu and interlace them and have a non-increasing sequence. So another way to define that is to say that lambda over mu, the skew diagram, is a horizontal strip, okay? And so maybe a lot of you have seen those before. If I take a sequence of n interlacing partitions, lambda n up to lambda 1, where lambda 1 interlaces with 0, and I keep with xi the difference of the weight of lambda I and lambda I minus 1, then what I get is a Shor polynomial indexed by lambda n. Okay, here lambda n is fixed and not in the sum. So now I'm going to talk in this talk about Rogers-Ramanujan identities. So they are not at all new identities. They exist for more than a century now. I don't know the exact date, but they are of this form, okay? So there are two of them that are very similar. Sorry about that. Okay, so here I have an infinite sum. I sum on n, q to the n squared plus n, divided by a finite product that I define here. Okay, and I get equal to an infinite product. Okay, and the other one is very similar, except that this plus n disappears in the sum. Okay, and the product here, I still have parts that are congruent to 5, but here I have parts that are congruent 2 or 3 modulo 5, and here 1 and 4 modulo 5. So by now, there's like lots and lots and lots of proofs of these identities. So I'm not going to give you the exhaustive list. Okay, but for now, at least, we don't have a very simple bijective proof of these identities. So that's what I call this type of Rogers-Ramanujan type identity. Okay, I have a sum here, okay, of basic hypergeometric identities equal to an infinite product with a certain modulo in the product. So sometimes people don't call that like that. They call the sum side as the fermionic side and the product side as the bosonic side, and proving that they are equal goes through the boson-fermion correspondence. But the classical way of seeing this identity, okay, is to interpret both sides, the left-hand side and the right-hand side, as families of integer partitions. So often the left-hand side of this type identities is what we're going to see as a difference conditions. Okay, we're going to define a family of partitions with certain difference conditions. And the way we interpret the right-hand side, the infinite product, as certain partitions where the parts are in a congruence class. So let's look at the example here for this identity. So you can see this, you can interpret this as the generating functions for partitions of n, where the parts lambda I minus lambda I plus 2, the difference between each pairs of parts is at least 2. And I forgot something, and no parts is equal to 1. And then the right-hand side, okay, is you interpret this as a partition also of n, the same integer, but the parts here must be congruent to 2 or 3 modulo n. Okay, and the combinatorial problem could be, can you prove a simple bijection between these two families of partitions? So let's take an example. So n is not 12, n is 10 here. So let's look. I don't know if you can see the bottom, but we have 4 partitions, where the parts differ at least by 2 and no parts equal to 1, we have the partition 10, 8, 2, 7, 3, and 6, 4. And on the right-hand side, we have also 4 partitions in 2 parts congruent to 2 or 3 modulo 5, namely 8, 2, 7, 3, 3, 3, 2, 2, and the partitions with all 2s. Okay? And you could ask yourself, can I give a bijection between these 2 sets of partition, not only for n equals 10, but for any n? Okay, so there exists some bijections, but none of them are very simple. And some people think that it's not possible to find a simple bijection between these 2 sets of partition. So today we're going to do a little trick. Okay, we're not going to look exactly as those Rogers-Ramanujan identities, but we're going to multiply the left-hand side and the right-hand side by the same thing. Okay, so when you think of identities, it's the same, but when you think of combinatorial objects, you're going to see that we find another family. Okay, so I'm taking that my same identity I had before. Okay, this equals to that, but I multiply the left-hand side and the right-hand side by 1 over QQ infinity. Okay, so basically I take the generating functions of integer partitions and I multiply both sides of my identity by this. Okay, so why is that interesting to do this? Is that Borodin in 2007 showed that now the product on the right-hand side is the generating function of certain cylindric partitions of a profile. So I will define right after what it means to be a cylindric partition and what it means to be a cylindric partition of a given profile. Okay, but what Foda and Welsh could prove also in 2016 is that the left-hand side is also a generating function for the same object. Okay, so now the combinatorics of finding a bijection is kind of trivial because the left-hand side and the right-hand side are the generating function of the same object. So that's what we're going to try to do today and generalize. Okay, so that's what I just said. Okay, now the bijective problem is kind of easy. Okay, not trivial, because it's not so trivial to show that the left-hand side and right-hand side are the generating functions for these objects. But you can find now a natural bijection to prove that this identity holds. So now let me define what is a cylindric partition. Okay, so this is an object that's been around for, I don't know, 25 years maybe or so. So it was defined by Gesell and Krathenthaler. So they define it in a more general setting. And today I'm just going to define them in the setting I will use. But you can check the paper of Gesell and Krathenthaler, and you can define like also some more restricted families. Okay, so my cylindric partitions, first I fix 2 integers, D and R. Okay, and I fix C, a composition, so a sequence of R non-negative objects, C1, C2 up to CR, and I want their sum to be equal to D. Okay, so it's pretty easy to count. Okay, the number of such composition is just a binomial coefficient. And in the rest of the talk, I will draw my composition, okay, as a lattice path. That way you can see again why this is a binomial coefficient. So when I have C1, C2 up to CR, I will draw C1 up step followed by an east step, then C2 north step followed by an east step, and C3 up step followed by an east step. Okay, so that's how I draw my composition. So here, what I draw here is an example when R is 3, D is 4, because I have 3 east step and 4 north step, and then the composition is 1, 2, 1. Okay, so that's what is indexing what we're going to call the profile of the cylindric partition. Okay, and then what's that cylindric partition? Now I'm going to take the path here and I'm going to fill the Ferraz diagram that's, I guess, all the cells that are here with those conditions that I must weakly decrease in row and weakly decrease in column. Okay, so that's my red entries here. I filled my 1-2-1 cylindric partition of profile 1-to-1 with integers that are red, and I want the integers to weakly decrease in column and weakly decrease in row. And now let me just add the cylindric part. Okay, so this would look like a plane partition or reverse plane partition. But now we have to see this object as if it was on the cylinder. Okay, and if I reproduce here the bottom row and I put it on the top, I must still have this weakly decreasing condition. Okay, so I take, this was my profile 1-to-1. Okay, and then I can recopy here and just, or I see it as a periodic plane partition, or I see it as an object on the cylinder. But that weakly decreasing condition in row and columns must hold when I add this cylindric. So from a composition, you can create what we call an interlacing world. Okay, so I have my composition C1, C2 up to CR. And so the same way I drew an up and east path, I'm going to write an interlacing world where I'm going to have C1 less or equal, followed by a greater or equal, followed by C2 less or equal, followed by 1 greater or equal, etc., etc. Okay. So my claim is that if I fix the profile here, 1-to-1, then I have a bijection between the cylindric partition of profile C and a sequence of interlacing partition. And the sequence is given exactly by my interlacing world. Okay, so how does that work on this example? Okay, I'm going to have lambda 0. I have C1 equals to 1. So I have 1 less or equal, followed by 1 greater or equal, followed by 2 less or equal, because C2 is 2, followed by 1 greater or equal, followed by 1 less or equal, and 1 greater or equal. Okay, and then when I wrap this cylindric partition, okay, that means that the condition I must have is that the first lambda 0 and the last partition must be the same. Okay, so let me try to show you why you have this bijection between this object that I drew in red and purple and these sequences of interlacing partitions. Okay, so this is easy to see if you rotate the diagram that I just drew. Okay, so I'm going to take this diagram and rotate it like that. Okay, and now rather than reading rows and columns that I was doing before, I'm going to read what was before a diagonal. Okay, let me do that on this example here. And now if I read now what are the columns of these tilted diagrams, I see really a sequence of interlacing partitions. Okay, so here I start here. My lambda 0 is 3. As I have an up step, it's easy to see that 4-3 is going to be interlacing with 5-4. Now I have a down step. So 5-4 is going to be interlacing with 5, but in the other direction. Now I'm going to have 2 up step. So 5 interlaces is less or equal to 6-1, which is going to be less or equal to 6-1-1. The partition I can read here, which is going to be greater or equal to partition 4-1, 4-4. And then we go back to 4-3. Okay. So just by rotating the diagram of my cylindric partition and by reading the diagonals, okay, I get a bijection between cylindric partitions that I could draw with my profile C and these sequences of interlacing partitions with keep in mind, okay, that the first one and the last one are equal. And so that's because we have this bijection between these cylindric partitions of given profile and these sequences of interlacing partition that we can get the generating functions for any profile. Okay, so that's a theorem due to Borodin in 2007. But with some Q-series techniques, this was also something that was in Gessel and Cratton-Taylor, even though it was not stated as is. Okay, so I fix my composition C. I sum on all the cylindric partition of this given profile. Okay, and I keep Q to the size of the cylindric partition. So the sum of all the entries in my cylindric partition. And for any C, okay, this generating functions is a beautiful product. Okay, because this is the sequences of interlacing partition. You can show that this is something that's always going to be a nice product. And what you see here is you look at the cells. So you have now an infinite number of cells, and you have to define that notion of cylindric hook. But this is really a nice generalization of something you could get for reverse plane partition of a given shape. Okay, so this is very a similar way, but now to see that on the cylinder. Okay. Oh, so maybe I made a typo. Let me go back. So when I recopied here, I recopied the whole row that was 5511, and I just recopied 5511.
Sorry, Sylvie, what were the dimensions of the rectangle?
So it could be infinite. So actually, the number of rows in red are fixed, but they could be as long as they want. And then I just recopy the bottom row to the top, just following the profile.
Could you hear the question, Sylvie?
No.
He asked, how did you know how far over to the right did you need to move it?
So because you repeat the profile, like if I have a, let me see if I have some room somewhere. So if my profile is 1, 2, 1, I'm just gonna repeat it again. 1, 2, 1. I just like repeat the profile again and again. So Sergi is proposing we move it R position. Yeah, it's. Sorry that I was not clear on that. Okay, so let's see why we care. And the link with Rogers-Ramanujan identities is that if we fix the profile to be equals to 2, 1, okay, I'm not going to give you exactly what that hook formula is you get this product, okay, that looks like the first Rogers-Ramanujan identities, okay, and if I fix, so that I rewrote here, so it's exactly the product that I see here multiplied by 1 over QQ infinity. Okay. And if I look at the ones that have profile 3, 0, okay, I get again the same thing as before, okay, the right-hand side of the second Rogers-Ramanujan identities multiplied by 1 over QQ infinity. So if I looked at composition of 3 into 2 parts, okay, the products that I get are the Rogers-Ramanujan identities. But what Foda and Welsh believed, and that's what we still believe, I guess, is that you could do that for any R and D. Okay, so if I fix R to be greater or equal to 1, I looked at cylindric partitions of profile C1, C2 up to CR. You can see the generating functions of these cylindric partitions of a given profile as a character formula coming from the WR algebra. Okay, and so they call it WR, but for some analogous, I'm going to say that if the profile for R, I'm hoping to get AR Rogers-Ramanujan identity. AR minus 1. So let me try to explain to you why we think that's what's the good way to go, okay, to try to get these AR minus 1 Rogers-Ramanujan identities for any R. Okay, so first, that's what they studied, Foda and Welsh in their papers. They show that all the compositions, when you fix R equals to 2, okay, so you get composition into 2 parts. The product side is always going to be of this form, okay? So here you can, if you take off this square here, you can interpret that as a certain generating functions for partitions. And what you get when R is equal to 2, I'm going to explain a bit, okay, are the Andrews-Gordon identities and their generalization by Bressoud. Okay, so now if R is equal to 2, we're going to have 2 families of identities. The case where the composition is a composition of D, where it's an odd integer. Okay, so now we don't have only a unique sum, but a multi-sum on the sum side. And then we get something of the same form as before, okay, so except now we have a k minus 1 multi-sum equals to that product. Okay, so that's what's called the Andrews-Gordon identities, and its companion identities is due to Bressoud, where now D is not odd, but D is even. And as you can see, they look quite alike, okay, except this term here is replaced, this QQ and minus 1 is replaced by a Q squared and K. And by changing this here, that changes the modulo on the product side. And so in their paper, Foda and Welsh showed how to look at all these compositions with 2 parts and relate those cylindric partition to this Andrews-Gordon-Bressoud identity. Okay, and what they did is exactly what we did for the Rogers-Ramanujan identities, is multiplied both sides by an extra QQ infinity. Okay. And again, they could show that the generating function of the sum and the generating function of the product correspond, what do I say? The combinatorial interpretation of the sum and the combinatorial interpretation of the product are cylindric partition of a given profile. Okay. So that's what I just said. Okay, you multiply by 1 over QQ infinity on both sides of the identities. Okay, and you find cylindric partitions on both sides. And so the big open question now is, how can you do for over R? Okay, so you'll have to convince yourself that R equal 1 is just a trivial identity. R equal 2 is going to give you the whole family of Andrews-Gordon-Bressoud identity. And how can we go higher? Okay, so how can we prove things for R greater or equal to 3? And so that's the conjecture that Foda and Welsh wrote down. And as you're going to see today, most of it is still open, is that we think that there's going to be a nice families for each composition you fix of C1, C2, CR of D. Okay, and it's going to be of this Rogers-Ramanujan identity. So what do we mean by nice? I guess what you want is this kind of things. Okay, so the product side is fixed. But the sum side, you like to have something where you have a multi-sum, where you sum some things that are manifestively positive. Okay, something that's gonna have some kind of combinatorial meaning. Okay. And so let me try to tell you a bit where we are. Okay, and so it's not exactly each composition. Okay, there's two tiny things that you can do to show that, for example, two profiles are going to give you the same generating function. Okay, the first thing is rotation. As we see the composition on a cylinder, okay, if you take the composition C1, C2 up to CR, you're going to get the same cylindric partition if you take the composition C2, CR up to C1. Okay, so you can do rotation. Okay, and all these 1, 2, 1, 2, 1, 1, and 1, 1, 2 are going to give you the same, I guess, conjecturally Rogers-Ramanujan identity. And there's another thing you can do, okay, because I said that I read the profile by reading my word here. So I had 1, 2, and 1, and I choose to read my word from left to right. But I can do a kind of conjugation of my composition, okay, and by reading the word from right to left. That would give me 1, 1, now 0, because I have just one step, 1. And so I have some also conjugation by reading my profile now, not from left to right and right to left. So except these simple things that you can do on your composition, okay, the hope is that you can get these nice multi-sum identities equal product for any composition. And so what we've done so far, okay, the main tool is to try to guess these multi-sums. What could they be? Okay, and so the simple idea we got with Trevor Welsh is now not to compute only the generating function that follows the weight of the partition, the sum of the entries, but also the maximal entry of the cylindric partition. Okay, so now I'm going to want to compute a generating function C, where Z is going to follow the maximum entry of the cylindric partition, and Q is going to follow the sum of the entries. Okay, so let's look at our example here that we've been using so far. So you can believe me, there might be a mistake though. The sum of the entries is 49. Okay, you sum all the entries in the cylindric partition, and the maximum entry here is 6. Okay, and the goal is to try to compute this generating function, hoping that they're going to give us hope on how to find these multi-sums. And so the theorem is very simple. The idea is simple. That doesn't mean that it tells you how to compute them, but you can find a sequence of generating function systems, okay? Because if you look at the maximum, it must be in one of the corners of the cylindric partition, okay? So you can use inclusion, exclusion. You look at a subset of the corners, thinking, is the maximum in this corner or not? Okay, you sum on all the subset, use inclusion, exclusion, and then you get an alternating sum of these generating functions with extra factors. Okay, so it's not so easy to handle because you see that here Z is changed to ZQ to the size of the subset. But at least that gives you a system of equations on how to relate these generating functions of compositions. So they're all composition of the same integer with the same number of entries. Okay, but that gives you a system of equation that you can try to solve. So in certain cases, it's very simple. So now I'm doing the case R equals 2, D equals 3. Okay, and you get this system of equation. Okay, but you already know what you're looking for, or you think you know, and you can easily check that as you have the condition that F of C of 0Q is equal to 1, okay, because there's just one empty cylindric partition. The only solutions to this system of equation is these two equations that I wrote here. And as you can see here, it's pretty nice because Z appears pretty naturally in what we were doing before for the Rogers-Ramanujan identity. Okay, so before what I had written was for Z equals to 1, but you see that Z comes naturally here in the product and also naturally in the sum. Okay. And then that helps you how to have a guess on how to do this sum. Okay. So we have a general conjecture on how this generating function should behave. So for any C and D, okay, the hope, and that's what the computer tells us, is that this bivariate generating function FC of ZQ is always going to be of this form, okay? So we're going to have 1 over ZQQ infinity, and then we're going to have a first sum on N, where Z appears here, and then it's divided by Q to the K, Q to the K, N, the product, where K is the, GCD of D and R. Okay, and then the second part here is going to behave nicely. That's the conjecture. Okay, so this part here is going to be a polynomial in Q into non-negative coefficients. Okay, it's always going to be a nice polynomial in Q into non-negative coefficients. And also, if we set Q to 1, okay, the value of the polynomial, so the sum of the coefficient of the polynomial, is always going to be nice. Okay, and what's pretty surprising, but maybe it's not, and that's something we don't know how to prove, is that it's independent of C. Okay, when I set Q to 1, the polynomial is going to equal to K to the N times 1 over D plus R times the binomial D plus R choose R minus 1 to the N. Okay, so now if I put by Q for any C, it's going to be different. But if Q is equal to 1, I'm always going to have the same number of the sum of coefficients. So what do we know so far? Okay, so we don't know too much. Okay, so for R equals 1 is trivial. For R equals 2, that's what I told you about Andrews-Gordon and Bressoud identities. And for R is equal to 3, so D equals 2 is back to the case where R is equal to 2, okay, because I can always switch D and R. D equals to 4 is what's called the A2 Rogers-Ramanujan identities. And then very recently, we did some progress in the case D equals to 5. So in a paper with Joandus and Unku, we could prove for every composition of 5 a candidate for the Rogers-Ramanujan identities. But right after, okay, Ole Warner proposed some other multi-sums that also gives this case D equals 5. So, and probably he has the good guess because he has then a whole family of conjecture that could generalize for any D when R is equal to 3. Okay. And so for R is equal to 3, the same that for R equals to 2, we had the 2 different cases where D is odd and even. For R is equal to 3, we are hoping to have 3 different families of identities, depending if D is 0, 1, or 2 modulo 3. Okay, so recently there was the first result by Tsu Kyo-choka, I'm sorry for saying that badly, okay, that does the case D is equal to 3. And so Ole Warner in his paper, he has a set of conjecture. He can prove a very small subset of them for some very specific composition. Okay, so you can see the composition that are of the form like nearly, the 3 parts are nearly equal. Okay, or the compositions where 1 part is equal to 0, 1 part is not too big, and the 3rd part is pretty big. Okay, and so, and even in those cases, there's just 1 or 2 cases that he can prove using representation theory. But for now, we don't have a proof using the cylindric partition. So let's see what is one of these conjecture of Euler-Warner. Okay, so that's the polynomial that I defined before. So that's for the profile k, k minus 1, k minus 1. Okay, and the conjecture is that we find again these multi-sum that are a bit like the Andrews-Gordon identities, except now we have two families of sums, n1 up to nk, m1 up to mk minus 1. So this, okay. So I think it should be ni plus 1. I'm not sure. Anyway, but we have like products of binomial and then some extra factors here, okay? And so for example, for that, we have a conjecture on how the multi-sum should behave. And also that, again, the maximal entries of the cylindric partition should help to prove this. And you can check that this should be F. That in this case, okay, the conjecture I wrote down before when we evaluate Q to 1 is true. So it's not straight away trivial to prove that, but you can prove it pretty easily. That this polynomial, if I set Q to 1, is going to give me 1 over 3k plus 1 times binomial 3k plus 1 to 3 minus 1 to the n. Okay. So that's quite remarkable, okay, that we can make such a guess. So that was our idea with Welsh to try to find like somehow what we call the true Rogers-Ramanujan identity, to take the generating functions of cylindric partition and divide it by like this one ZQQ infinity and try to compute this GC of ZQ. Okay, but this year recently, Kennedy and Russell decided to look at another way to put a product in front of the generating functions of cylindric plane partition. And they chose to do it this way, okay, and find some other type of results that are not exactly what we would call Rogers-Ramanujan identities, but that are, again, this kind of multi-sum equal to product, okay? And they succeeded in quite some ways. So if R equals to 3, you actually get back some results of Andrews, Schilling, and Warner that date back from 2002. And that would correspond to, again, composition with a part equal to 0, a small part, and one large part, okay? And then they could use computer algebra to prove these identities for any composition, but now when D is less or equal to 7, okay? And then Unku very recently went just one step further and could prove and find these identities for D is equal to 8. Okay, so that's what we've done so far. That's what we know. And I'm not going to give you any details about proofs and things like that, but I want to highlight a couple of things. Okay, so the first idea to look at this problem is to look at it as a combinatorial problem. Okay, to find these identities, we try to prove that they are the generating function of certain combinatorial objects that are the cylindric plane partitions that are defined by a given composition. Okay, then from this point of view, now we go to these bivariate generating functions where we don't only follow the weight of the cylindric partition, but also the maximal entry on the cylindric plane partition with the idea, the conjecture, that this will help you to find the sum side of this identity. Okay, then we can write now this kind of system of bivariate generating functions and use Q-series techniques and computer algebra to try to find the sum sides of this identity. So let me just give you an example. So for example, when R is equal to 3 and D is equal to 5, that's the system of generating functions that you're trying to solve. And as you can see, doing it by hand, at least me, I don't know how to do it, okay? But now there's some beautiful computer algebra techniques to try to use these. So first you can triangulate the system. So rather than write this G of 3 to 0 as depending on overcomposition, you can find some equations where G of 3 to 0 is only going to depend on G of 3 to 0, but with some like changes in Z. Okay, and that's the difficult part we have so far. And that's the difficult part we have so far. You need to be able to make a guess, okay? And if you can make a guess, you can ask the computer if he can prove that the guess you made follows this system of equations. Okay, so that's what we had done for d equals 5 and n equals to 4. Okay, we made a guess that the sum side was of this form, and then the computer could give an automatic proof that this corresponds to one of these equations. Okay, but for now, we don't have any way to do that in a more efficient way or more clever way. And of course, because you do that, you can only prove it for very small d. Okay, you can see that already for d equals 5 and r equals 3, the system is really big and the computer cannot go further. But we need to keep in mind that all of these come from like character formulas, okay, of affine Lie algebras, okay, and the very recent paper of Su-Chio, yeah, is really used based on Lie theory, okay. What he does, he finds some like level 3 module of the affine A2 Lie algebra, okay, and he constructs the multisum using Lie theory. So the hope now is to try to go and combine all these approach, okay, using a mix of combinatorics, Q series, these automatic proof, but also go back to the algebra and put everything together to find and go further and prove all these identities, I don't know, for any composition, C1 CR of, okay. So let me just give you a very what I call a lovely special case. Okay, so if I look at the case d is equal to r plus 1, okay, so when r is equal to 2, that would be d equals 3, and these were the two Rogers-Ramanujan identities. Okay, so the conjecture is because of the cylindric action is that we are going to have Catalan R Rogers-Ramanujan identities. Okay, and they are all going to be on the form like this 1 over QQ infinity. Okay, then I'm going to do a first sum with a nice factor here, a nice polynomial with coefficients that are going to be non-negative. Okay, and then I'm going to use Borodin's formula to find this product of cylindric hook. Okay. So that's the conjecture that this polynomial is always a polynomial in non-negative coefficient. But also, okay, oops, when I evaluate this polynomial at 1, okay, then I find again the Catalan numbers. Okay, so this polynomial FC of N for C, a composition of R plus 1, when I evaluate it at 1, it's going to be the half Catalan number minus 1 to the N. So that's the hope. Okay. But that's only that's open for r is equal to greater or equal to 4. So it's a conjecture that we believe true, but kind of a dream. And so what we've known so far is only very, very simple polynomials, you know. So when r is equal to 1, the polynomial is trivial. Okay, it's equal to 1 if n equals to 0 and 0 otherwise. When r is equal to 2, these are the Rogers-Ramanujan identities. And you can see that these two polynomials are equal to 1. Okay, when R is equal to 3, we have 5 Rogers-Ramanujan identities. Okay, and if you look at the polynomials that come up, if I evaluate them at 1, they're all equal to 4 to the n. Okay, but when R is equal to 4, I already have no idea on how to construct this polynomial. So that's the big challenge for you today, okay, is how can we guess those multi-sums? Okay, so I said now we could, one way is to go back to the fact that it's coming from character formulas and use the leaf theory. That's one of the things that we think that would be a good way to do, like through like the recent papers for D is equal to 3. But also what I would like from a combinatorics audience is try to find more statistics on the cylindric partition where we could only not follow the first sum, but follow several sums in those multi-sums we're trying to build. Okay, so for example, for the Andrews-Gordon and Bressoud identity, Bressoud had found some statistics on path to understand all the entries in the multi-sums. It was called like some kind of relative height or something. But on these cylindric partitions, for now, we don't have a good idea on how to look at different statistics on the cylindric partition that could help us to find what could be in each sum of these multi-sum identities. Okay, so I'm gonna stop here, and I'm sorry that I was not there, but I'm still happy to have given this talk.
So we'll take questions from the audience first, and then we also, it sounds like we have some questions in the chat as well. Joe? Could you hear that, Sylvie?
No.
Okay. He asked about affine and Hellman and Grossel, but let me RSK versions. But let me...
Yeah. Hi, Sylvie. So thanks for the nice talk. So there are these affine versions of RSK and Hillman-Grossel that maybe can let a person turn a cylindric plane partition into other kinds of objects like periodic integer matrices or affine permutations or something. Do you think that those might be helpful for statistic hunting, or is that?
Oh. Oh, yeah, that's a good idea. Yeah, I haven't thought about that because I always thought about those as giving you the product side, but maybe that's a good idea. Yeah, so I'll look into that. Thank you.
Thanks.
Those two people
I don't know who asked the question.
Oh, that was Joel Lewis.
Okay.
Other questions for Sylvie? I think Nathan had a question in the chat as well.
Yeah, hi, Sylvie. Thank you for a very nice talk. I just have a very naive question. Is there any way in which one can see, root systems of type A somehow hiding in these equations? We're doing something in type A, or is that just sort of the wrong approach, the wrong way to think about it? Especially maybe in these special cases where there are Catalan many equations. I wonder if there's some root system thing going on.
So actually, that's probably a good idea, but I don't know the answer to this question. But it's probably yeah, it's something to look at, definitively.
Thank you.
Other questions for Sylvie? If not, I guess we will thank her again, and then we'll invite graduate students to come down to the front to chat with her after.